Hello everyone, and welcome to CRAMsurg, Clinical Research Appraisal and Methodology for Surgical Trainees, where we pick a paper fresh from the press on a hot general surgical topic. We review it for you, we present it for you, we critique its methodology for you, and provide top-of-the-field expert opinion and teaching on research appraisal and methodology. My name is Gio Perin, and together with Professor Sababala Subramanian and Maria Digby, we bring you CRAMsurg from the wonderful region of the Yorkshire and the Humber.
Excellent. So, as we did last time, we're going to talk about statistical tests today, and I'm going to talk about students' t-test and a brief chat on scarcity and what it means. So similar disclaimers to last time. I'm not a statistician and I'm not an expert in stat software. I read about both, and I kind of do a little bit of both every now and again and when I can. Let's start with a brief summary of what we did last time. So last time we introduced the concept of assumptions, what they are, and to very briefly reiterate, they are a relevant piece of information about your data, and a rule that must be fulfilled in order for the test that you're choosing to do to be valid. We talked about probably the most important assumption out there, the assumption of normality of the data, and how to look for it and how to test for it, which again we did last time by simply looking at the numbers, looking at the way the data shows on a chart, and also doing a Shafiro-Wilk test. So today we're going to carry on our plan. We're going to carry on continuous data, and we're going to look at normally distributed data. In particular, we're going to look at the two groups, and particularly we're going to look at a t-test for non-paired samples. And we're going to do that again using Jamovi as a demonstration. So a little bit of history for myself and for this test. These are my two university professors of statistics and the people that introduced me to the students' t-test and its history. So I thought I should give them a shout out here. They used to have a picture with themselves in front of the Guinness factory, but I couldn't find that one, I'm afraid. So why the Guinness factory? Well, because students' t-test was born out of work that was done at Guinness a long time ago, now over a century ago. And it has to do with barley quality testing and making sure that the beer that comes out of your factory is of good quality, which we all know is very important. So basically, the question that people at Guinness were asking themselves is, I have two batches of barley. How do I find out if they are different without testing every single grain? And that's where all the story about students' t-test started, particularly with William Gossett. And as I said, this is a very old story, starts in 1908. And Gossett was a pioneer of quality control and quality assurance, if you like, in the brewing industry, but also in other contexts, you would say in statistics in general. And he published a paper in Biometrica. If you Google Biometrica students' t-test, you can still find his, obviously, a PDF copy of his original paper. And when he published the results of his technique, because of very strict rules that were imposed at Guinness at the time, he couldn't use his own name because Guinness was worried that other breweries and other industries would steal their industrial secrets. So he published it using the pseudonym Student, hence why the test is called Students' T. So to translate the problem about barley into something a bit more generic, we could say that the problem that student was trying to sort out was, I have two samples representing two independent populations. How do I know if they're truly different from each other? And as we said, this is roughly where we sit in this context. And I mentioned earlier on, we're going to talk about non-paired t-test because the samples that we're talking about come from two different populations. And we'll have an example of that. What does it mean when we talk about paired samples? Well, it means that we effectively are taking a piece of data from, for example, the same person at 2 different points in time. For example, I take a sample of 40 men, I measure the blood pressure, then I give them a tablet to correct it, and then I measure it again. Those samples are paired. They're associated with each other. Let's talk about the assumptions that lie behind the student's T. So, as we said earlier on, some truth about your data that have to be fulfilled for you to reliably run the test and for the test to give you a reliable result. So the assumption number one is normality. So we talked about it, and it is pretty much always the first assumption you need to check for. So I'm not going to go into too much details about that. The second very important assumption has to do with skedasticity. Particularly, this test should be used only if your data is homoskedastic. What does that mean? Well, it means that the variance of the populations that you're testing fulfill a certain rule. I'll try and give you a graphical example, very simple. You can have two identical populations. They have the same mean and they have the same variance as the one you see on the left. You can have two populations. As you can see here, they have the same mean, but they have a different variance. You can have a population that have different means, but have the same variance. Now, in order to use students' t-test, you have to be in the rightmost situation. So your two distributions have to have a comparable variance. The test is, as they say, robust to a degree of variation from this truth. However, if the variances are really different between the two populations that you are trying to compare, you shouldn't be using this test. You should use something different. So homoskedasticity is the scenario to the right. Okay. There are further assumptions that are probably relatively logical. The samples have to be randomly extracted from the populations. The samples have to be big enough. Now, how do you define big? This is a bit more difficult. If you look around, most of the opinion seems to say that if you have at least 40 observations per group, you should be able to use this test and it should be reliable enough. And the two samples, as we said, they have to be non-paired. So a quick recap before we go into a practical example. To use this test to determine whether two populations are different, we have to have two samples of continuous data from such populations. The data has to be normally distributed, and the two samples have to have comparable variances. So let's go back to my dissertation data set as we discussed last time. As part of my dissertation, I collected some data about papers that were advertised on Twitter by the publishing journals. So the question I'm asking today, and I'm trying to answer is there a difference between medical and surgical papers in terms of retweets? So I've got a continuous variable, the number of retweets, that I have collected for medical paper and surgical papers. And these two groups are different from each other. So it's a non-paired test. So let's have a go. Similarly to last time, we're going to load this lovely data set. I apologize for my voice today. Unfortunately, I have no control over it. So let's start with something very, very simple, right? Let's check, first of all, if what we want to do makes sense in terms of our assumptions being fulfilled. Let's start by doing some data explorations and some descriptives. I said that I wanted to see if retweets are different between medical and surgical papers. So I'm going to pop retweets here, and I'm going to split it by surgical or medical. And Jamovi straight away gives me a bit of information, as you can see. Probably the thing I want to look at first is this data normally distributed? What's the difference between mean and median? Well, it's pretty massive. more in medical papers rather than in surgical papers, but still pretty massive. So this data is probably not normally distributed. We can see that even more if we use a histogram, even if we do a bit of density there. You will see straight away that the data is skewed. We can do more things here. We can check variances. As you can see, put it there. There is a slight difference there, as you can see. And you can also do that. It will give you additional information about the data. Okay. Now, let's assume, and obviously we can run the Sheffield-Wilk test as we did last time, which suggests that, again, the data is very much not normally distributed. But for the purposes of doing this demonstration, we are going to ignore all of this and pretend that the data is normally distributed. And we're going to move on to do a t-test. And we're going to do an independent samples t-test. And similarly to what we did a second ago, we're going to take the tweet and we're going to put it here. And we're going to take our surgical or medical as a grouping variable. We're going to put it there. And as you can see, Jamovi spits you out a beautiful p-value. It does also give you a fair warning that probably this is not the test you want to run on these samples. And you can also check for assumptions. Particularly, you can do a normality test, which is what we did last time, straight from here, very handy. You can also do an homogeneity test, which is a test that checks if the variance between the two populations that you're studying is similar or not. And as you can see, it definitely isn't. So we have seen how easy it is to actually run a sample, a t-test. We've also seen how easily Jamovi tells you to be careful about the data you're analyzing and how he prompts you to look for your assumptions and making sure that you're taking them into account, which is one of the reasons why I love it as a software, because it's very easy to teach and to understand also what's behind it, what's behind all the statistics, at least to an extent.
Thank you everyone for tuning in and listening. Until next time, keep running your life with our surgical podcast.